connected and our audience on YouTube is also there. Okay. Yes. So, welcome to today's NFDI talk. This episode is about Aruna, a federated data orchestration platform for life science and beyond. And I welcome two speakers here today. Our speakers are Jannis Schlegel and Sebastian Beyvers. Jannis Schlegel is a research assistant at Giessen University with a strong interest in scientific data management, particularly with distributed systems. Currently engaged in the NFDI initiative, his work centers on harmonizing data ecosystems at a national level, advancing collaborative research infrastructures, and efficient data sharing practices across disciplines. The other speaker, Sebastian Beyvers, is a distributed systems researcher in bioinformatics and a cloud-native Rust developer at Giessen University as well. Sebastian's current work focuses on cloud-native data storage and processing solutions that try to harmonize existing national and international data ecosystems, such as GaiaX and NFDI. Welcome, Jannis and Sebastian. I'm happy to hand over to you now.
All right. Thank you very much for the kind introduction, and thank you for having us here and giving us the opportunity for this presentation. And we will present to you today, as you already said, Aruna, a federated data orchestration platform for life sciences and beyond. And for everyone here in the audience who hasn't had the pleasure until now to interact with NFDI for microbiota, I will also give a short introduction. NFDI for microbiota focuses on managing, standardizing, sharing, and supporting microbiology, microbiome-related research and research data through a variety of repositories, workflow support, a knowledge base, so knowledge sharing, also training, and of course through building integrated, and I think this is one of the keywords, sustainable infrastructures and services. NFDI for microbiota has the vision that researchers at the end can easily leverage this infrastructure to translate their research data into, I would say, a deeper understanding of their research field without having to worry about cost or complexity of setting up their own analysis infrastructure or even renting it. NFDI for microbiota is consisting of 10 partner institutions and has been acquired through national and international connections over 50 additional participating organizations, which brings together a very broad spectrum of expertise from microbiology, bioinformatics, data management, and of course infrastructure development. And as you can see, NFDI for microbiota already has a rich ecosystem of infrastructure and different domain-specific services. So the challenge here is not that nothing exists. NFDI for microbiota is also involved in overarching consortia, overarching interest groups, which are called the biodata and biomed interest groups, which has come into existence after the observation that despite different scientific focuses of the consortia, there's at least some overlap when it comes to the methods, the data types, or requirements for research data management between these consortia. And with this, I will take this opportunity as a shameless plug to advertise the Boosting Biodata Bootcamp, which is the annual conference of NFDI for microbiota, which is held this year, the first time for jointly with other consortia from the biodata interest group. It's from September 15 until September 17 at the RWTH Aachen University. And to the right is a QR code where you can register. Registering is free, and there will be a lot of interesting talks. And yeah, if anyone wants to meet the Aruna team or feels inspired to have to participate in a hands-on workshop with the Aruna team, this will be the perfect opportunity for you. All right, back to the talk, and let us first take a look what microbiology research, what the process of microbiology research looks like. So just to get an image of the whole journey from sample taking till the publication at the end. In this illustration, we already start with the wet lab. Actually, beforehand, the samples must have been taken somewhere, but we will start in the wet lab where the researcher prepares the samples following specific protocols, having first analysis, and yeah, already producing some kind of data and metadata, which is then captured hopefully in some kind of electronic lab notebook. The outputs from the lab instruments and the experiments, they are processed by themselves. Some of the samples are also sent to external sequencing facilities, which then produce a large amount of sequencing output, a large amount of digital data, or samples are also sent to other laboratories which are more specialized in specific experiment and assays, for example. Further analysis then happens or can happen across a variety of compute environments, for example, beginning with lab notebooks or just laptops, processing with local scripts, small workflows, checking things, up to institutional servers where, for example, the institute has some kind of infrastructure where a Jupyter Hub is deployed, where the analysis can be happening in Jupyter notebooks, for example, up to, for example, project workspaces in the cloud where the processing happens on high performance compute clusters. Also, external inputs are kind of important in the scientific process, where the raw generated data is enriched with additional data, for example, from reference databases or other public repositories, or, for example, domain-specific services which provide additional contextual data for the analysis. The complete analysis produces lots and lots of output, not only the final output, but also intermediate outputs, which are, in my opinion, or should not only in my opinion, are pretty important, especially for provenance context. Something that is continuously in the scientific process here is the collaboration with other people inside the team, outside the team, working in different project workspaces. You have data sharing between institutions, tools, different infrastructures, and towards the publication, then curated and selected data set gets created, which contains the data which fits the research and the repository where it should be deposited the best, which then provides a stable accession access for the publication. And I think you're noticing where I'm going with this, as this shows that in general microbiology research is a very diverse and complex discipline. So with all the subdisciplines and everything, there is a lot of going on with the data and metadata. You have lots of different data formats, lots of different metadata formats, metadata schemas. But not only this, as I already said, analysis landscape is also pretty complex, not in the sense of from laptop up to high performance cluster, what is the best for my analysis, but also, for example, the handling of different data is pretty diverse. So public open access data has to be handled differently, very differently, for example, in difference to clinical patient data, which should be handled strictly confidential, for example. There are also many well-established repositories which are scattered around the globe. And also, as I already said, microbiology produces large volumes of data, not only in size, but also in regard of the number of data points, which can also become an issue pretty fast. We do not also have only the complexity part, but also you have seen that the scientific process in microbiology has a lot of moving parts. So there comes together the different participants, the different tools, the different services, different storages, different infrastructures, and all of this together leads inevitably to some kind of fragmentation, and not for one thing, but only for data, metadata, and also the provenance aspect. So as an example, metadata, for example, can live in electronic lab notebooks. Then there's maybe some left in spreadsheets on local hard drives, on other notebooks, something subdirectories of some institutional servers, or it is spread across some cloud documents when collaboration with other institutes is happening. Additionally, maybe the metadata is defined by different custom local conventions or repository-specific schemas, if a metadata schema is applied at all, hopefully. Files or data generally move between lab PCs, sequencing centers, storage systems, are processed in workflow engines, other compute sites, and so on and so on. This leads to duplication of files, renaming, provenance loss if all of the steps can't just be reconstructed, and intermediate outputs and, for example, failed runs can be scientifically meaningful, but at the end are rarely captured in the final repository records, which brings us back again to the repositories, which are very important and valuable, not only at the end of the research process, but also in between. But most of them require a specific set of metadata and also have relatively strict requirements which data is supposed to be in the data packages that are submitted to them. And so from all of the information that was generated in such a research project, this gets condensed pretty hard, and I think only a fraction of this data is then at the end selected for the result data sets, or in other words, when the data gets submitted into a repository, most of the time the provenance gets lost, for example. And with this, the repository more or less answers the question at the end where a submitted data set is, but now, for example, Aruna helps to answer the question then where it came from and what happened to it. And this brings us now to the point, or the question, what actually is Aruna? And already said in the title of the presentation, Aruna is a federated data orchestration engine. But what does this mean? Instead of stitching all the participating or moving parts in such a project together in some kind of centralized platform, Aruna works as a federation of sovereign and independent nodes, which are, for example, positioned before and around repositories and other data infrastructures. But it's not limited to this. It would be just the first step. And with this, Aruna connects these distributed data and metadata into a coherent technology layer. So with this, you can track provenance from the start. And as I already said, it's not replacing repositories, and Aruna itself is not a repository. Aruna manages the scientific path that leads to the repositories or data infrastructures. So Aruna is motivated by the idea of being an organization and integration layer for scientific data that provides a unified model for data, metadata, provenance, discovery, synchronization, access control, and all of this in a flexible way so that can be adapted to nearly every scientific discipline. And Aruna does all of this without forcing everything through a central hub, which would always mean giving up bits and pieces of sovereignty and independence. So in this network, everyone is on the same level and this has always the hand on their own infrastructure. And with this, we will dive a little bit deeper into the feature set of Aruna, and this is where I pass the presentation on to Sebastian.
Yes, thank you, Jannis. Thank you for the neat introduction and the description what microbiology research means and how Aruna fits in there. I think one important step, a little bit to go back here and a little bit to describe here is the problem we had was there were so many laptops, so many HPC clusters, so many infrastructures scattered around, and we wanted to find a solution to connect them together and to integrate them into one coherent system without interrupting the existing infrastructure that is already in place. So we don't want to replace an electronic lab notebook, we want to connect with it. And we don't want to replace a Slurm cluster with a Ceph storage backend behind this. We want to connect with this. And this leads to our current design of Aruna, which is the new design. The Aruna version 2 design was a little bit different, where it was a little bit more centralized and there were some centralized aspects of it. But our current design is completely federated. And what we mean with federation is we have sovereign independent nodes that collaborate together and build a data space or build a system that handles data commonly and together. And you can deploy the new version of Aruna everywhere. You can deploy it on a laptop, on a server, in a Kubernetes cloud environment, wherever you want. We don't restrict that, and all of these nodes can interact and collaborate with all the other nodes. From a technical perspective, they are all created equal, and this has a lot of problems from a distributed systems research perspective, because you then must think about how can we have consistency over a federated system where nodes can join and leave whenever they want. How can we create a structure that feels coherent for a user? And this is the thing we have been working on for the past 3 or 4 years, because these are not easy things to solve, because having a central instance is always the easiest part, but maybe not the best part for the future. And the idea in this collaboration instance is to have a realm. A realm is more or less a mutual agreement between different nodes that they want to work together. And this doesn't really mean that the realm has central control, but there are some mutual agreements like, okay, we want to do something for a specific topic like microbiology research and so on. And each node then can have some rules on top of that that enforces local specific rules that only apply to a specific instance, a specific laptop, and a specific computer that runs the node itself. And this way we can also scale really well. We can just add more nodes however we like, and by adding more nodes we can scale that horizontally how much we want, because it's quite organic. Just add a few nodes and then the realm gets a little bit bigger. And this makes it quite convenient to use for users, because they just run Aruna on their local laptop. It connects to the whole system, and then they can say, okay, my data is now here locally available, and I can put it somewhere else, or I can use it on a cloud environment for compute, and then I get the results back to my laptop. And because my laptop is not really the best place to store the data permanently, I can also configure, okay, I want to have two replicas available on different nodes, one on the cloud environment and one on a different site or something like that, so that you can have some replication available, which is not really a replacement for a backup, but which gives the system a little bit more resilience in the long run. Which brings me to the next slide. On the next slide, the main thing we wanted to have is we wanted to integrate as many data sources as possible. So we want to have all the data that's flying around integrated into Aruna, or at least referenceable in Aruna. And for this, we have an agnostic storage backend built into it. It uses a library called OpenDAL, which is a universal storage plug-in backend that can connect to a lot of storage providers that are available, from Google Drive over Nextcloud to FTPs, Postgres databases, S3 backends, you name it. So everywhere where you can put a file, you can integrate it with OpenDAL, and this is built into Aruna. So you can say, okay, my data lives here. And with this, you don't really need to configure the data itself or import them or something like that. You've in the first step, you just need to say, okay, my data is here. And then you can do something with this. You can, in the Aruna node, reference the data and say, okay, I only have a reference to a reference database or something like that. And then it's just a link to somewhere else. Or you can do a snapshot. You can say, okay, give me the current version of this data and import it to my local storage, because I'm not really confident that the remote location will stay in place. Or you can say, okay, sync it periodically, or you can even say sync it only once it's fetched once. So for example, you have a huge reference database in microbiology research, for example, the RefSec or something like that, which consists of thousands of reference genomes. And in most analysis, or at least in some analysis, you only need a fraction of them, because you are interested in a specific organism or a specific group of organisms. But your workflow may want to have the full RefSec available, and then pick only a few of these files out for your local compute. And with this, you can say, okay, I have a reference to the full RefSec, and only if you request this, it gets copied over or linked to the local machine, so that it's available and fast on fast local storage. And you can also say, okay, in the future, after a certain amount of time, it will get deleted. So you can cache data from a remote location on your local node if you want to do that. Or you can just reference it and download it each and every time when you want to access it, which has some drawbacks, because you need to do everything on via the internet, but you don't really need to have the data locally available for that. And for the external part, Aruna exposes an S3 interface. So we use an Amazon compatible S3 interface. So users and existing tools and existing infrastructure can connect to that. And in the backend, it's a generic backend you can configure in that. And these S3 buckets are then composed together by the user. So the user can say, okay, this bucket contains a few files from the local node, a few files from a remote location. And for an external tool that connects to that, it feels like a normal S3 bucket, because it doesn't really know where the data lives. And Aruna handles where the data lives and where the data is resigned, and how the data should be moved around. And this leads to a lot of concepts we can do with that. We can do data to compute, or we can compute to data with that. So because we know where the data lives, and we know how huge the data is, and how complicated it is to transfer the data around, or we might even know that there are some certain restrictions. Some data sets can't leave a certain location or something like that. We can decide where to compute a certain workflow. So you trigger a workflow and submit it to Aruna, and Aruna knows, okay, this step needs the following part from a reference database and the small file you provided, and the reference database is available on location X, and then it can just ship the one computational step to the place where the reference database lies. It computes it there and puts the data back, and then it can compose together the workflow by where it best fits and where the least overhead is necessary to move the data around, or where it's required from a legal perspective because the data can't really leave the location, or because it's confidential data, and so on. And with this, you can decide where your copy of your data lives. You can say, okay, the data stays on my laptop and it stays there forever, which is not really the best from a security perspective or from a data retention perspective, but some users might prefer that. We don't really restrict that. You can do some policy rules on a realm level. You can say, okay, on our realm, it's required to have at least three replicas available on different locations or something like that, so that you can have a governance on top of that enforces something different. But from a technical perspective, you can do whatever you want with that. And data is copied from A to B via verified data streaming. So we use something called Blake 3 verified data streaming. And this is quite efficient streaming of data that checks the integrity of the data while it receives the data. So you don't really need to receive the data and compute the hash afterwards, because Blake 3 is a composite hash that is built on top of each and every bits and pieces, each and every packet that's sent. You can, after each packet, validate that this is still the correct data coming in, and you are in the end sure that the data that you received is the data that you requested. Yes. For us, data is immutable. So our S3 implementation uses versioned S3. So when you overwrite the data set, in most instances, you get a new version of that, and the old version is still accessible. This way, you can't really lose data, and you can't do the oopsie daisy moment like, okay, I removed my important scientific publication data. You can't really do that because you can just overwrite that. In practice, you can do that if you want to force it, but for legal reasons, this might also be the case. But from a technical perspective, in the first place, everything is immutable. And with this, you can rerun old analysis, and you can capture old analysis and reproduce them. If you use a reproducible workflow with fixed pinned versions, you can check that the exact data, input data with the exact output data matches if you rerun the workflow itself. Data in our world is completely content addressed. So the identifier of a data set is its content hash. So the Blake 3 content hash. It's similar to like P2P systems or torrent systems. You distribute data around in the world. And like BitTorrent, for example, uses a similar system where you have the content hash, which is the identifier of a data set. And we have policy on top of that, how and when a user can access the data and can't access the data. And if you have access to a specific content hash and you can prove that you are the owner of a specific file with a specific content hash, you get access to this even on nodes where you didn't really grant it the data, if the policy allows that. So with this, we can do some deduplication. For example, you have one data set that's copied all around the world 10,000 times, and it's always the same content, then it can in the end be deduplicated to just one copy that's laying somewhere, or one copy with 3 replicas or something like that. And because we know the content hash, we can also verify the content on each retrieval and make sure that the data that's shipped to the user is the correct data, at least from our side. ideally the user itself via S3 means or something like that needs to also verify and double check that the data is correct from their perspective. I talked a lot about data, and this form of data is mainly let's phrase it blobs, so binary large objects. So this is data that is files or everything that lives on your hard drive. And we also want to capture metadata. And for this, we use research object crates. I think many people have heard about this, which is a compact storage and packaging format for data and metadata. And we use the detached form with references to our data links. And with this research object crates, we can have it in under the hood. It's just a JSON-LD, and we use this JSON-LD on our nodes to destructure the JSON-LD and build somewhat of a knowledge graph out of this, because it's just triples in the end if you destructure the JSON-LD. And we destructure this on our nodes. So if you put a research object crate to us, for example, ELN files from popular ELNs are also just our crates under the hood, and you can import them, and it will just be destructured to a knowledge graph, and then you can query it via normal knowledge graph means like Sparkle queries and all this kind of stuff. But we focused on the research object crate packaging format, or at least representation format for the most part, because it's quite convenient and quite flexible to integrate, and it's easy to work with for normal users that don't really want to deal with the whole Sparkle knowledge graph section. And we extended our system with a full text search. So if you have a description or any full text field in that, you can also search about that. And the search is distributed over all or over a certain selected set of nodes, so that you can get a meaningful result for your search. And each update to the metadata and the data graph produces an event, and this event is stored in a long graph of event lists. And with this, we can have a full provenance, what happened to which data set, who added which field, who did what to when, and when did this happen. And we can also roll back to a specific point in time. Because research object crates are quite flexible and quite usable for many research domains, we also integrated metadata profiles. So you can say, okay, my research object crate requires the following fields from the following ontology, and so on. And with this, you can say, okay, I want to have certain metadata objects that comply to a specific format. And there are also existing formats already available. For example, there's the workflow run crate from the Elixir bioinformatics community. There are a few others from the language community in Australia. I think they have quite vibrant community around our crates. And so we choose this format as our main entry point to and from our metadata, because it's widely integrated, and I think it will get even more integrated in the future because it's so flexible and so easy to use. And we can, in the end, have either the raw crate metadata JSON-LD file exposed to the user if they want to work with this, or we can also package the data and the metadata together like a traditional crate, where you can have all your results and all your things bundled together to share with someone else, for example. And also other NFDIs are also working with these metadata formats. I know, for example, that Dataplant uses their ARCs, and they have an ARC to crate converter exporter. And so we try to use some interfaces that are widely accepted and are good integratable into a wide range of fields in the NFDI. On top of that, we want to provide catalogs. So via standardized catalogs interfaces, we want to have a data catalog, what is available, because these all these crates that we publish or that we reference are sometimes not enough. You want to have standardized cataloging interface, and we are currently working on having some harvesting infrastructure built in. So like ORE, OAI, PMH is one of the standard metadata harvesting interfaces, and we also want to support DCAT, for example, in the future as a standard and widely accepted, internationally accepted, and EOSC accepted cataloging interface. Yes. On top of that, users are realms can choose an identity provider. So this is more or less, or nodes can choose that, but in the end, the realm itself can choose that. And we wanted to have a wide range of identity providers, and so we choose OIDC, so OpenID Connect, as our protocol for that. And you can configure the identity provider of your choice, or even multiple of them, for your realm to identify users. We also worked with the ERM for NFDI to have a seamless integration with the ERM groups. This is currently not integrated in, it's still working in Aruna version 2, but this will soon also follow for the version 3 as an integration. You only need one Aruna identity for all your realms in theory, because Aruna identities can also be federated. It's similar to the matrix protocol, where you log into your home realm and get an identity that can be used on another realm. And this way you only need one login. And when you choose your login, you will get redirected to the specific home realm where you want to log in. And but you can also have multiple identities, and then you must merge them, or you can merge them to one identity with multiple login points. Access control is managed by role-based access control. Straightforward how many things are doing. So you can define groups and have rules, and rules define certain permissions and obligations on specific paths, and you can say, okay, this user only can read data on this path, or in this bucket, or on this metadata path, and so on. And on top of that, we also wanted to have custom policies that are way deeper, where you can say, okay, this request or this metadata request requires the following fields, or users must be whitelisted to do something in this specific domain or something like that. And for this, we integrated common expression language. It's still missing in the front-end web UI, but it's coming soon. With common expression language, you can create expressions like, if the user has an age of above 18, he can do that, or any of these. You can use attributes however you want to access data, or only users from a certain group, or with a certain email or whatever can access data. You can be really flexible with common expression language, how and when a user can do something. Yeah, I think I've talked about that. We use as our front end for uploading data. We use an S3 interface. For uploading metadata, we have a REST API or a Sparkle endpoint, where you can also create metadata. We also integrate with some Elixir interfaces. There is the data repository service, or where you can have some RESTful access to data, because sometimes this is quite convenient with workflows. And we have data cataloging interfaces. I think I've talked about this as well. So in the end, what can you do with Aruna in this stage? You can find your data, you can track your origin, you can share your unpublished data. You don't really need to copy data around, at least not manually. You don't really need to put something from this folder and that folder, because Aruna can do all of that for you. And it can also track when have you done that and why have you done that. It can trigger processes and workflows. It can sync data to specific other locations, and it can also have enforce certain redundancies. It can know what the data is, mostly via metadata, and you can in the end publish the data via integrated publishing services or repositories, and then you get a persistent identifier from the repository for that. But this doesn't really mean that the data is lost. You can still reference it from the internal ID, or it gets an alias for the external accession number or DOI or whatever the identifiers is provided by the repository. The most important thing here is adoption of Aruna doesn't really need to be from now everything must be integrated into Aruna. It can be gradual. You can start with one thing and play with it around and look how it fits in your research workflow, and then you can gradually integrate more and more of your research workflow. And we are also working quite hard with more integrations like ELNs and all this kind of stuff, so that we can have a more seamless workflow where we can import and export the data for the users. Currently, there is a lot of manual configuration still in place, but in the future we want to simplify that with more pre-built integrations that are more or less plug and play to make it easy for users to integrate their data. And with that, one little outlook, this is not really specific to scientific domain like life sciences. As I've said, our crates are also heavily used in literature research and all this kind of stuff. So you can adopt something like this that in many places. If you have something like files lying around, I think there is not really much more to have. Then you can start with that. You can do really good cross-domain collaboration with that. You can increase the discoverability of your data and the tracing of your data and the sharing of your data with partner organizations or collaborators, because sometimes this is quite inconvenient if you want to share data on your local HPC system with someone that's outside of your local HPC system, and then they need an account, and there's a whole bureaucracy laying around there. And in the end, we aim for Aruna to be part of the one NFDI, because it can be really convenient and helpful for connecting all the storage NFDI for storage locations that are now built and integrated, because having them all distributed around and not really connected is not really that feasible. And I think in the end it would be quite nice to have at least some connecting fabric that connects all the storage that's available, at least to some degree, together, and build one coherent ecosystem how users and participants can connect their data and store their data and retrieve their data and bring them however they want to their research workflows or to their final repositories. A little bit regarding this, so Aruna version 3 currently has about 1 million objects stored, 18 terabytes. There's quite a lot of data still missing, and still we halted a little bit of migration effort because we now worked on version 3 and we want to migrate all of that to version 3. We have above 50 users from four NFDI consortia, so it's not only microbiota, it's also biodiversity and a few others. Currently, we are testing Open Alpha version 3. It's still work in progress, but we hope that there will be a open beta at least somewhere in this year. Some of these changes were done because the first funding period ended, and we migrated to the second funding period and wanted to have some changes that users brought to us, and we wanted to integrate these changes as well. And with this, if you want to give it a try, there is v3.aruna-engine.org. You can just register there an account and just play with it around. As I've said, it's an alpha. It's not really there are still some visual front-end bugs. We firstly focused on the complex distributed systems topics, and hopefully we will present to you more in the future. And if there are questions, just let us know.
Yeah, thank you so much for this interesting introduction into Aruna. Yes, I would say thank you to Sebastian and Jannis for this interesting talk. Before we say goodbye on YouTube, I want to tell you guys about the next episode of the NFDI Talk, which will take place after the summer break. We'll have a little summer break over the month of July and August, and we'll be back on the 24th of August with a NFDI talk in German this time, and it will be on data protection, science and research, whether that's a contradiction or an opportunity. And if you're interested to hear in that, tune in on August 24th. With that, I will stop the stream and say goodbye on YouTube. Second. Yes. Okay, now it's only us in the